Engineering Mechanics Statics Lecture 13. The present lecture will critically review the third subchapter, which is equilibrium of a rigid body. For the first part, which is condition for rigid body equilibrium. The objective is to identify support reaction and draw a free body diagram of the support reaction. So this is the application. Let's say a 200 kilogram platform, like in the picture here, is suspended off an oil rig. How do we determine the force reaction at the joints and the force in the cables? So previously we only have a force externally exerted on the structure, but for this time, if we have a joint like this and like this one, so how we want to consider the force on those joints? So how are the idealist models and the free body diagram used to do this? Which diagram above is the idealized model? Okay, which is the idealized model? This is the idealized model, and this one is a free body diagram. So you can apply this to do your project also. First, you need to capture the actual picture of the structure, and then you do the idealized model like this. Okay, so finally you will come up with the free body diagram. Okay, that's for the project. And for this one, we need to study about how to determine the reaction force in the joint here. Okay, any type of joint. There are so many type of joint. Okay, so how we define it? So for example, if we have a joint here, so we gonna have a reaction force in the x and y direction, and if we have a joint that attached to the string like this, so we gonna have a force in a tension of spring like this. Okay, so that's how that's one of the example how we interpret the force in a joint. So our focus here is to know what we call it as support reaction force. Okay, which normally we define this in a joint of structure. Okay, joint, which mean it's connecting between maybe more than one structure. Okay, so let's say your system involve a support structure, and then each support structure will produce what we call as a reaction force. Okay, let's say if we have a joint support like this. Okay, so this is your structure. Okay, so you have let's say a force from the structure this way, coming this way. So the joint here will produce also a force that we call it as a reaction force, and then the direction of the reaction force for this type of joint is normally have two components, which is denote it as AX and AY. Okay, to differentiate between the reaction force and the normal force, like this one, normal force like this, so we denote it as A. Okay, so because it is the normal force is not either on the x or y direction, so the reaction force here will have two components in the direction of x and y. Talking about the direction of the reaction force, actually the direction of reaction force follow the direction where the support or the joint prevent the force from the structure. Okay, let's say the force from the structure in this direction. So when the support prevent the structure is that way, right, against the direction of force, so automatically the reaction force will have the same direction of the prevention of the joint or support. Okay, in this case the joint here. Okay, now let's look at some other example of the joint. Normally we have a joint like, for example, like this one, like some kind of spring here. Okay, this is one sort of support or joint also. Okay, so this one, if the normal force is this way, so to prevent the normal force here, so your reaction force will be in that way. Okay, so it will simply, your reaction force will be like this. Okay, and then another one example, if we have a joint like this, but this time it is not, the base here is not fixed, it has a roller like this. Okay, so this is your structure. So this one, your reaction force will be in that way. Okay, or it has the same model like this. Okay, so this one is also not fixed, so your reaction force will be normal with the base here. Okay, one more example I would like to show you is the difference between this joint and this joint. It has a pin, and this one is directly fixed on the wall. Okay, this kind of support, you will have a reaction force like this. Okay, X and AY. But this one, you have a reaction force of AX and AY, but also a moment here. Okay, so they have three reaction here, which is force and X and Y direction and the moment here. This one got no moment because it is pin, so it's free to rotate. Okay, but this one it does not have a pin, so it has a tendency to rotate. That's why it has a potential force of moment. Okay, so this one have no moment because it free to rotate. Okay, that's the difference. So other example of support or joint, you can refer to your textbook. So they have a list here, so you need to remember or you need to understand how the reaction force is working. Okay, this is one of the lists, and then the other list, okay, and then this one. Okay, so and then this is the last one. Okay, so this is for two-dimensional. For three-dimensional, we also have the list. Okay, we will learn in the next lecture. Okay, so please study the list here. Okay, now let's go back here, go back to this slide. Okay, if we have a structure like this and then we convert it into the idealized model like this, okay, so from the idealized model, then you will define the free body diagram of the idealized model. Okay, so in this case, if you have a joint or support in your structure, so you need to consider the reaction force within the joint and then the other force lah. Okay, so let's say in this model you have a reaction, you have a joint here and then a support here, and then the weight of the platform itself. So your free body diagram will become like this lah. In your joint you have a reaction force like this, and then the support reaction in this direction, and then the weight of the structure itself. Okay, so that's all the force that involved in this model. Okay, so that's how you define your free body diagram. Okay, let's recall a bit about condition for rigid body equilibrium. If you want to do analysis of free body diagram, for for particle analysis, previously we have learned there's two type of analysis, which is particle and rigid body. For particle, we only have a force like this. We won't have a condition of moment in this way. But for rigid body, you need to consider a moment because there is a line of action from the any arbitrary fixed position here to the force. Okay, so that line of action, that combination of line of action and the force will cause the rigid body to have a tendency to rotate. Okay, so that's the thing you need to consider when you want to do a analysis of free body diagram. Okay, or you want to draw your free body diagram. Okay, let's have some exercise here. Let's say we need to draw a free body diagram of the uniform B, like the one shown in the figure here, and the beam has a mass of 100 kilogram. Okay, so how we want to convert this idealized model into the free body diagram? Okay, so previously I already explained so you need to consider all the, if you want to draw a free body diagram, you need to consider all the force involved in this structure. Okay, the first one is of course the force here, the external force here, and then the second one is the weight of the rigid body itself or the beam here, and then the third one, is there any joint or support involved with so you need to consider that also. So in this case, the support or the joint is the one is beam is attached directly on the wall here. So when the support is like this, so the support there is a support reaction occur in this beam, in this wall and the beam. So the support reaction will be will become like this. So you have a force in the x and y direction, and also you have a rotation here. You have a moment here because the beam have a tendency to rotate. But if the beam is rotate freely, there is no tendency to rotate, so there is no moment here. Okay. So so if you get a step here, draw an outline shape. Imagine the body to be isolated or cut free from its constraint and draw its outline shape. So you draw the outline shape of the structure here. Take out all anything that any other things than the structure. Okay, and then the second one is show all the external force and couple moment. These typically include apply force. Apply force is the force here, and then the support reaction. The support reaction is this one lah. And then the weight of the body itself. Okay, the weight of the body. And then the third one is label load and dimension. All known force and coupled moments should be labeled with their magnitude and direction. For the unknown force and coupled moment, use letters like AX, AY, and MA. Okay, indicates any necessary dimensions. Apply the equation of equilibrium. Another one example here, if you have a structure like this, okay, so you need to draw the free body diagram of the structure. Okay, the step is the same. So the first one is draw an outline shape. Okay, so draw only important structure. So, okay, the structure that has many force exerted on it. For this case, this structure, okay. So it has a force here, it has force here, it has force here, and then any other structure you need to take out other than this structure. Okay, so only draw this structure. That's we call it an outline shape. And the second one, show all the external force and coupled moment. And the third one is label load and dimension. Okay. Okay, so your outline shape is this shape, this one. Okay, the shape that has many force, that has all the force. Okay, the force of the weight of the structure itself, and then the reaction spot here. Sorry, the reaction joint here, and then the reaction spot here. Okay. So also identify all the unknown, which is X, AY, and TB, and then do the analysis of equation of equilibrium to find all the unknown.